Here's an interesting mechanics problem which was given to 10th graders this year in 2024 at the Romanian National Physics Olympiad. So in 10th grade, usually students are around 16, 17 years old, and the Olympiad has, or the theoretical part of the National Olympiad has 3 problems, and this one was part capital A of problem 3. Okay, so if you have any suggestions, if you would like to see any particular problems from a particular year that was given to the Romanian National Physics Olympiad or any other Olympiad, let me know in the comments. So let's try to read this, let's try to understand it, and then we'll try to solve it. So we're given a profile, a 2D profile from figure 3.1, which is not labeled, but it's this one here. So this is figure 3.1, which consists of a descending slope AB. And by the way, I should say that I asked ChatGPT to translate from Romanian to English because I wasn't bothered to do that myself. So in any case, so this profile consists of a descending slope AB, which continues with a circular arc BC and then is connected to another circular arc CD. Okay, both circular arcs have the same radius R, and it's known that at the point of connection being point C, right, because there's arc BC and arc CD, so clearly C is the point of connection, the tangent small delta to the 2 arcs is common. Okay, on this contour, a point mass M moves without friction. So this is kind of like a roller coaster, if you want to, think of it as a more fun problem. And we have to answer 2 things. So the first one is determine the minimum height h from which the point mass must be released so that at some moment it detaches from the profile. Okay. So I'm not going to read part small b yet. We'll, you can do this yourself if you want, and we'll do it afterwards. So if you want to try this yourself, if you're one of the students who participated this year from 10th grade, well, I hope it went okay for you. If you want to know how to, well, if you want to try this yourself, pause the video and give it a try, and then I'll try to answer it moving forward from now. So for part A, we have to find the minimum height from which the point mass must be released so that at some point, right, at some moment, it detaches from the profile. So let's try to understand why this detaches from the profile at all. So we've got the object is at a certain height. There's no friction anywhere in this problem. Yeah, we're told that this is an important thing to know. There's no friction, and the object is going down the slope, and then it's traveling down this sort of like convex circular arc, and then there's a concave circular arc, and then we are trying to figure out why it detaches. So first of all, I'm gonna make the bold claim that the object will never detach before it reaches point C, right? Yeah, I'm not gonna go into a deep proof, or maybe I will, I haven't decided yet. If, for example, if we think of the object being at an arbitrary position, somewhere here or somewhere here, we can actually try to understand what happens. So let's do like this kind of mini proof that the object will never detach before reaching point C. So let's say that you're in this section, in this convex section, which is like holding water kind of the path. So we have the object is here. Let's say it has some velocity, but if we try to draw the free body diagram, so we have a couple of forces. So we have mg let's use straight lines like this. So we have mg, which is acting down. We have the normal reaction force as well, which is acting like this, and there is no friction. So actually those are all the forces that are acting. The other thing is that I should decompose this weight into two components, right? So we have a component of weight which is parallel to the local slope, which is based on this angle theta, right? So this is mg sine theta, and then there's the normal or the perpendicular component, which is mg cos theta. Right, now what's happening in this case is that this object has a normal acceleration, and the normal acceleration is like this, right? And this normal acceleration, we know it's given as v squared over r. So, you know, in those circular arcs, the radius is constant, so that's useful to know. The velocity is not constant, because the object is either gaining height or losing height. So there will be a discussion about potential and kinetic energy, which we're going to talk about in a second. But we have the normal acceleration, and we can write Newton's second law along this direction. So we can say that n minus mg cos theta is equal to mv squared by r. So the normal reaction force is therefore mg cos theta plus mv squared by r, which we can factorize m if you want, so we can do this. And this is always positive, okay? As long as the object is on the convex circular arc. So there is no reason why this would ever be negative, right? So the object will never detach before reaching point C, because until point C, the path is the path looks like this convex circular arc. But after point C, things start getting a bit more interesting. So let's look at what happens from C to D, kind of, if the object even reaches D, as you'll see in a bit. So let's say point C is, I don't know, somewhere here maybe, and let's say that the object has managed to reach this point, okay? So when the object is here, again, we're going to draw the free body diagram. So we have mg, we have n, which is the normal reaction force like this, and that's it. So those are all the forces, there's no friction. Now in this case, the object is actually accelerating in a different way. So the normal acceleration is acting, well, it's still perpendicular to the slope, but you can compare it to how it was on the convex part of the path and how it is on the concave part of the path. So now the Newton's second law actually is going to look a bit different. So we have an angle theta between the forces. So this is mg cos theta, and then this is, of course, this is mg sine theta. Okay, so we can then write that mg cos theta minus n is equal to mv squared over r. So look how it looks here. So it's mg cos theta minus n, and this was n minus, so there's a difference of being multiplied by -1 kind of, and the reason is the curvature of the path has changed in sign, basically. So we can rewrite the normal reaction force as mg cos theta minus mv squared by r, and this is m times g cos theta minus v squared over r. Now this is a problem, because this can be negative. Well, it's not going to be negative, but it can be 0. So this is able to be 0, and when this is 0, the object is no longer in contact with the ground, essentially. And this is what we have to figure out. So we have to figure out the minimum height from which the point mass must be released so that at some point it detaches from the profile. So we know that it can detach from the profile anywhere from point C onwards. Now, if this object is released from a height that's not big enough, so if we release the object from, let's say, from here, it may not detach at all because it won't be able to catch enough speed, because it's the speed that decides whether this will detach or not. Because if you look at this equation, right, you have g cos theta, and g cos theta is constant for a given angle, right? But v will change based on the height, and the higher you drop the object from, the higher the velocity for a given angle theta. So eventually, when those two quantities are equal to each other, then the normal reaction force is going to become zero. And that's basically it. So let's try to figure out when this happens. And the way to do this, the easiest way to do this, is to use energy conservation. Okay, so what I'll do here is I'm going to write the initial energy of the object. So the initial energy, which is going to be E1, is going to be made of potential energy at 1 plus the kinetic energy at 1. Now there's no kinetic energy at 1, right, because it's dropped from rest. So this is just EK1, which is, sorry, I said there's no kinetic energy at 1, so this is EP1, which is mgh. Okay, so this is the total energy that the body has stored, kind of. And now what we'll try to do is we're going to try and figure out what the energy is going to be, or we're going to find the expression of the energy, because the total amount is going to be the same, when this object is, get rid of some of the stuff, when this object is at an arbitrary position on that concave part of the slope. So when the object is, let's say, here maybe. Okay, so let's try to draw some angles. So what I have here is that the angle between this object and the vertical, I'm going to call this theta, because why not? So this is my angle theta, which is arbitrary for now, right? And I'm going to say that at this point, the object will detach from the surface. I don't know where this is, I don't know what theta is, but you know, I'm just saying, without any loss of generality, that at this point, the object will detach from the surface. So let's try to figure out what's the velocity of the object at that point, because we need the velocity, remember. This normal reaction force, to be zero, we need V. So let's find what's the energy of the object at this point. So I'm going to say that the energy at 2 is going to be equal to, well, the potential energy at 2 plus the kinetic energy at 2. I didn't mention this before, but I'm taking the ground as my zero potential energy level, but I think it should be clear by now. So in this case, the potential energy at this position is going to equal mg, and then this is multiplied by essentially the vertical projection of the radius, kind of. So I'm talking more specifically about this distance here, which that distance, actually I can write it in I can describe it in a more accurate way, is given by this right triangle, and it's the, it's that vertical bit from here to here. So that's the height above the ground. And of course, if you do some trigonometry, that's going to be mg multiplied by r, okay, multiplied by cosine of theta. plus, and now we have the kinetic energy, which is just 1/2 mv squared. So I don't know what v is, but we're gonna try and figure it out in this way. Okay, so let's make the energies equal to each other because we have energy conservation. So we have mgh equal to mg, and then we have r cos theta plus 1/2 mv squared. We can cancel the m's like this, and we're gonna get v out of this, which is what we wanted to do. So we get v squared over 2 is equal to g times h minus r cos theta. And I'm gonna rewrite this as v squared is equal to 2g h minus r cos theta. I'm not gonna square root because I don't need to square root. The v appears as squared in the expression of normal reaction force, so there's no point to get v by itself. So let's write the normal reaction force again for the concave part of the path. So we have m g cos theta minus v squared by r, and we said this is equal to 0. So when this is equal to 0, it implies that g cos theta is equal to v squared divided by r, like this. So we get that v squared is gr cos theta. So when this happens, the object will no longer be in contact with the surface. And now we have two expressions for velocity. So we have the one in red and pink, which this comes from energy conservation. So this one has nothing to do with the object leaving the surface or not. So, you know, this is the velocity of the object at that different height. And this one here, this is the velocity of the object just when it leaves the surface. So we have two expressions of v squared, so we can make them equal to each other to create this scenario when the object is detaching. So we have h minus r cos theta is equal to gr cos theta, and then we can cancel out the g's, and we have 2h minus 2r cos theta is equal to r cos theta. So we can get that 3r cos theta is equal to 2h, which means that h, because it's h that we wanted, if you remember. So this is 3r divided by 2 multiplied by cosine of theta. Okay, we're not done yet because we still have to deal with this. Okay, so the question was, what's the minimum h? Let's go back to the question. What's the minimum h? So this will detach at some point. So let's think about this. We're trying to minimize this expression of h, which is 3r over 2 multiplied by cosine of theta. 3r over 2 is a constant. Cosine of theta is not. So if we want to minimize h, we have to minimize the cosine. So we want to find when is this cosine, you know, as small as possible. So if we think about trigonometry, you know, if you think of the first quadrant, obviously cosine is so the minimum value of cosine is 0, yeah, and this happens when the angle is pi over 2 or 90 degrees. And now we have to think, can we use this in our example? Well, in our example, actually, there's something interesting that's going on, because this object, you know, it can go up to a theta value, well, I should say it can go down to a theta value of 0. So when the object is here, theta is 0. and the cosine is 1, which is not really what we want. We want the cosine to be as small as possible. And if the cosine is as small as possible in the first quadrant, remember, it means that the angle has to be as large as possible. So this is the key. Now, the angle theta does not ever go to 90 degrees, because when this angle theta is 90 degrees, our object is here, right? And this angle here would be 90 degrees. But at this point, the object is not actually on the concave path. So we have to look at what is the largest angle, and the object has to be on the concave path as well. So what's the largest angle such that the object is still on the concave path? So the answer was given to us, well, was disguised as this mention of the tangent. So this point C here, this is the point that joins the convex part of the path and the concave part of the path, and that's where the object is entering this concave section where it runs the risk to detach from the surface. So if we find that angle, whatever that is, so if we find this angle, which is, I'm going to call it alpha, that's the maximum possible value that theta can have. So I'm going to say here that theta max is equal to alpha, where alpha is, it's that angle. So let's try to figure out what alpha is. And how do you do that? Well, I think we can use some geometry, because remember, you have two circular arcs which are joined together. So actually, this pink radius is perpendicular to the tangent delta, and then I can extend this like this. So that's not the right color. I can extend it like this as well. So those radii from the two circles O1 and O2, they join together, and they're like, those two radii are basically parallel to each other as well. So this line from O1 to O2 is made of, it has a length basically, which is 2r. So let me try to bring this here again and try to examine things a bit closer. So what I have, as I said, is if I join those centers, I get point C basically. And my goal is to find the angle alpha, and I think we can do that quite easily, because we know that this is a right triangle, and we know the hypotenuse, which is 2r, and we know that angle alpha is here as well. So we can do, I think we can use not tan, but we can use cosine. So if we use cosine of alpha, that's going to be r over 2r, which is equal to a half. So that's nice. So alpha is pi over 3. It's a nice number. Radians, of course, or 60 degrees if you prefer it this way. Okay, so that's it. So we found alpha, which is pi over 3. So our theta, for h to be minimum, theta has to be maximum, and the maximum value of theta is when theta is equal to alpha, and the value of alpha is 60 degrees. So if I go back to the formula for h, or for h min, I should say. So this is 3r over 2 times cosine of theta max, which is 3r over 2 times cos of pi over 3, which is a half. So the final answer is 3r over 4. Yeah, and that's part A. So if we drop this object from a height which is equal to 3r over 4, 3r over 4 being, so this is r, basically, this height here is r. So if we drop it from 75% of r, right, so where would that be? So this is 50%, this is 75%. So if we drop it from here, this point, this object will detach, and it will detach at point C. It will not see the rest of the slope. Well, it will see the rest of the slope after it falls. And we'll talk about falling in part B, because this is where things get interesting, more interesting even. So let's talk about B now. From what height must the point mass be released so that after detaching, it hits the profile again at a point that is at the same height as the detachment point? Interesting. So basically, we know that the height that we're using for B has to be at least 3r over 4, because the object has to detach, like part B is telling us this in the face. So from what height must the point mass be released such that after detaching, this object hits the profile again at a point that's at the same height as the detachment point? So that's interesting. What that means is the following. First of all, I'm gonna put this diagram here again, so give me 1 second. Trying to not lose any significant amount of quality when I do that. Okay, I think this is good enough. So what I've got going on for me here is the diagram, which basically, if our object is released at, from any height above 75% of r, it will always detach, and it will always detach at point C. Right? And I don't think this requires any more explanation. So if you release the body from here, from the minimum point, so this is h min. So this is h min. Yeah. So if you release the body from here, it will detach at C. If you release it from anywhere higher, it will also detach from C. Like, it won't have enough. Well, the speed will be too great when it gets at point C, if you release it from anywhere higher, to do anything, to be able to travel along the slope or along the arc from point C onwards, if that makes sense. So if it can't stick to the surface from h min, there is no way it will go beyond point C if you release it from anywhere higher. Basically, that's the idea. Now, the interesting thing, another interesting thing, is what happens after it leaves the surface. And I think this is where this question becomes interesting, because this kind of question, like part A, I've seen this many times, like, where does the object detach from the surface? And we have to find the angle, or we have to find the height, and we're done. But part B is asking something beyond that, and it's asking us to look at what happens when the object is going, is detaching from the surface. Like, what kind of motion does it have? And let's try to think about it. So we know on one hand that those are the centers of the two circles, and this is where this is point C, where the object is detaching. And at this point, the object has a velocity, clearly. So it has a velocity, and that velocity is always tangent to the path, because that's, that's part of the definition of velocity, like this. And if it's not on the surface anymore, if it's not interacting with the surface, if n is equal to 0, then the object will be in free fall. Well, not free fall per se. It will be under the influence of gravity. So you can call that free fall if you want, but I think a more accurate description would be projectile motion. So from point C onwards, this object will not be on the path anymore. So it will be in midair and it will undergo projectile motion. And depending on the value of v, this projectile motion could look in different ways. So the subsequent path of the object could be, it's going to be a bit tricky to draw. It could be like this, right? It's going to be like a parabolic path, or it could be something like this. Or if v is too high, because there's no limit on how big h can be, and if there's no limit on h, there's no limit on v. And in that case, you can have the object like do something like this, and it falls like way beyond this path and so on. But none of those paths are actually interesting to us. The one path that we actually have to study and investigate is the path which not only brings the object back on the circular arc, but brings it back on the arc at the same height that it started from. So in other words, this object is going to land. We have to make this object land at this point, which is, so this is C, this is D, we can call it E, I think, like this. So we have this symmetry going on. So the object is leaving the path at C, and it has to have enough speed, but not too much, because if it's too much, it can go completely off the circular path. It has to have enough speed to land at point E, right, where point E has the same height, the same elevation as point C. So that's quite an interesting problem, I think, now. So we have this part A when we found what's the condition of the object detaching, and then there's part B where suddenly we're dealing with projectile motion. And well, this is what we have. So let's try to figure out what the velocity has to be. And then we're going to work backwards, kind of. So we know that from energy conservation, we can find velocity. So if we have the height, we can find velocity, but it works backwards too, right? So what we're going to do is we're going to find v, and then through energy conservation, we're going to find h. Okay. So let's see what we can do. We know the angle of the velocity here, so we know this is 60 degrees, right? So we know this angle is 60 degrees, or pi over 3. So that angle has to be the same as this angle. Okay. So I'm going to decompose that velocity, as it's the case usually, into this horizontal component, which is v. You know what, actually, I'm going to change this. I'm not going to call it v, I'm going to call it u. So I'm going to call this u, and I'm going to call this u cosine of pi over 3, or u cosine of 60. I think that's a bit more common. Okay, so we have this, and we have this, which is u sine of 60. Okay, now because of symmetry, right, there's no air resistance or anything like that. So because of symmetry, we're pretty sure that the highest point is going to be coinciding with the same vertical as the center of this circle. So the path, if you want to kind of have an idea how it looks like, I'm gonna try to draw it, but it's gonna look a bit bad, I think. It's gonna look something like this, maybe. Okay, that's a bit, went a bit off. So it's gonna look like this, more or less. Yeah, so the peak is gonna be here. Okay, so let's try to figure out the equation of motion, and based on that we can then find the velocity u that it started with. So we can use the Soviet equations quite easily, I think. So we can say that for the x direction, the horizontal distance, which is the distance from C to E, right? We say that x is equal to u cosine of 60 multiplied by the time. And then for the y direction, we can say that y is equal to, so if we use this this CE line as our datum, we get u sine 60 times t minus g over 2t squared, right? And I'll get rid of the sine and the cosine, so that gives us u times 1/2 times t, and y is u root 3 over 2 t minus g over 2t squared, and I think we can take g as 10, I think, but anyway, actually I'm not sure if that's the case, so I'll leave this idea for now. Okay, so this is x and this is y. Now what I'll do now is I'll find the time from this equation, because I know that when it at landing the y value is equal to 0, right? So we can say that 0 is equal to u root 3 over 2t minus g over 2t squared. So what I'll do is I'm going to remove a t because I'm not looking at the initial time. So I know this eliminates a solution, but I don't care about that initial solution. So I have u root 3 over 2 is g over 2 t. So we can therefore say that time is equal to u divided by g multiplied by root 3. Okay, I think that looks fine. And then we sub this in here. So we have x is equal to u times 1/2 times u over g root 3, which is u squared over g times root 3 over 2. So all we need now really is to find what's the horizontal distance, which shouldn't really be difficult to do. We just use some trigonometry and we'll figure it out. So the distance to CE is given by that kind of like opening, and we know this angle is 60 degrees or pi over 3. We know this one is also 60 degrees or pi over 3. So we can find what CE is in that case. So CE is equal to, this is going to be equal to r sine of 60. I think that looks fine. So r sine 60 times 2. So this is going to be equal to 2r root 3 over 2, which is r times root 3. So that's the horizontal distance that we want. So we have r root 3 is equal to u squared over g root 3 over 2. The square roots cancel out, and we end up that u squared is equal to 2gr. And that is it. So that's the velocity of the object. That's the initial velocity of the object that it needs in order to land at the same altitude that, or at the same elevation that it started from. So now we're going to work backwards and use energy conservation to find the height. So let's recap. We have the initial energy is mgh, and we have the final energy, or the energy at point C or at point 2 or whatever. That's 1/2 mu squared, because now we called our velocity u, plus mg, and this is going to be r times cosine of 60, right? So that's cosine of 60, and I think we're almost done. So we have mgh is 1/2 mu squared plus mg r times 1/2, and that gives us that, okay, let's do it on a separate page actually. So mgh is equal to 1/2 m. Now, instead of u squared, we're going to use the value of u squared, which is 2gr. So this is 2gr plus mgr times 1/2. So we have mgr multiplied by 1/2, and there's a lot of stuff that cancels, which is great. So the m's go, the g's go as well. So yeah, we don't care if it's 9.81 or 10 anymore. So it doesn't matter on which planet you do this experiment, in other words. So h is equal to, this is 1/2 times 2, which is just r, plus r over 2, which is going to give us a value of 3r over 2, which is a nice round number, I would say. So whoever made those problems was a nice person, and you know, used numbers that didn't really need use of calculators, because you know we have that 60-degree angle, and that opened up some really nice values in the end. So anyway, that was the problem. So we had to deal with energy conservation, we had to deal with centripetal acceleration and what's the detachment condition, and then we had that you know, even further we peeled off that layer and we ended up with projectile motion. And then in the end we started with the projectile motion and we worked our way backwards. You know, we used energy to find out what the height was for the object to have this special property that it leaves the surface at C and it ends up at E, which is a point with the same elevation. I hope you enjoyed it, and if you want to see something similar, let me know in the comments. But for now, yeah, that's the end of the question.